Hello, everybody. So, this is a podcast on equilibrium. So, equilibrium is a type of chemical reaction where you go in the forward direction and then you go back in the reverse direction. It says here, describing equilibrium, virtually all chemical and physical changes are reversible. For example, we have NO2. So let's say we have NO2, it's a gas. We throw it into a closed container. Okay, we throw it into a container, some sort of vessel. And these NO2 particles are going to collide. And when they collide, they're going to trigger a chemical reaction. And in this case, it's going to form N2O4. So we normally write reactions in this way, where we write the starting material on the left and the products on the right side with an arrow here pointing to the right. That's what we're used to. But again, virtually all reactions and physical changes are reversible. So you can actually reverse the chemical reaction if you place it in a closed container. So if we look at this here, we see a symbol that looks very different. This is called the equilibrium symbol. It's like a half arrow pointing to the right and a half arrow pointing to the left. What that means is that you're going to produce some N2O4. And then once you have enough N2O4s for collisions to occur, then the N2O4 can go back in the other direction, in the reverse direction. And when you have both occurring at the same rate, then we call that equilibrium. So what is so equal about equilibrium? It's the rate. Okay, the rate. The rate of the forward reaction is equal to the rate of the reverse reaction. Okay, so here is an example of what is happening. You guys can read that on your own. And I'm going to summarize this using graphs. So here it says, eventually the forward and reverse reaction rates become equal. The concentrations are stable, but not equal. So the rates are equal, but not the concentrations. And to show that more clearly, I'm going to draw a graph. So right here, we're going to draw two graphs showing what is happening at equilibrium. Okay, so we're going to draw what is happening with respect to time. So again, let me just repeat myself. You have NO2. You are throwing that into a closed system, a closed vessel, a closed container, and you're going to produce this product, N2O4. And then once you have enough N2O4, then you're going to go back in the reverse direction, and eventually the rate of production of both substances will be the same. However, the concentration is not the same, so we're going to illustrate that using a graph. So we're going to put concentration on the y-axis. So this right here, these symbols, means concentration. And I hope you guys remember that concentration is typically written in moles per liter, right? So the graph is going to go like this. And then at the bottom, you guys will write time. And NO2, so let's start with NO2. You have a bunch of NO2, and then it's going to stabilize. Okay, so this right here is going to be NO2. And you're going to produce N2O4. So at the beginning, you have a lot of NO2. So you have a lot, and then it gets used up. And it gets used up because you want to make some of this guy. So at the beginning, you don't have product. So you start here at 0, and then you're going to make product, and eventually it'll stabilize like that. Okay, so this would be the production of N2O4. Okay, if you look here, the concentrations are not the same, they're different. So look, they're actually very different. Okay, but once it begins to stabilize, that point where the concentrations are stabilized, then we call this equilibrium. Okay, so equilibrium starts there. It starts right here. So you have constant amount of NO2 and N2O4. Constant does not mean same amount. Okay, it just means it's just stabilizing and they're not equal. Okay, so this is how you would draw a graph that represents the amount of a reactant at the beginning being used up, and then the production of a product, and then stabilizing. So this is how it would look like. Now I'm going to do the second graph, which is this part right here. Reaction rate. So how fast is your forward reaction occurring and how fast is the reverse reaction occurring? So for that other graph, we're going to start with our axes. We're going to put rate on the left side and time at the bottom. Again, our reaction, you could write it again if you want. NO2, you could do the arrow that way as well. And N2O4. So at the beginning, you'll have a lot of NO2, so you're gonna have a huge drop in NO2, and eventually the rate becomes constant. Then the rate of production for the N2O4, it goes up, and then it becomes equal to that of the reverse reaction. Okay, so this represents the forward reaction rate, and this would represent the reverse. And if you see here, the point at which both lines intersect or overlap, we call that equilibrium. So equilibrium is established here. Okay, so equilibrium is established there, where the reaction rates are the same. So the forward and the reverse reaction rates are the same. Okay, even though the concentrations of both are different, hence the first graph we drew. The big ideas are right here, so go ahead and read them on your own. That was the theory, and here's more. You guys can read this on your own. And what I'm going to show you right here are two examples of equilibrium. My first example is an example of a saturated solution. So if you guys remember what saturated solution means, it's that you have a solid and some of these solids may dissolve, and if you add more solid, then it'll keep dissolving, but eventually it'll stop dissolving. And when these solids stop dissolving, we say that the solution is saturated. So here's an example. We have NaCl, which is salt. Let's say we have a solid, and the solid ends up dissolving, right? You end up producing Na plus and Cl minus, right? That's aqueous. But sometimes these guys right here will end up joining forces again. They're going to form an ionic bond. And so the reverse reaction can occur as well. And when you have both the forward and the reverse reaction occurring at the same time and at the same rate, then we say that equilibrium is established. So if you, inside the box, you guys should draw this. This is what it would look like. So let's say you have some NaCl. So let's represent one circle as Na, the shaded one, Na. and then Cl as this guy. So here are NaCls, you have a bunch of them, and then they start to dissolve, right? They start to dissolve, right? And then these guys end up joining together, forming an ionic bond, and then they go back in the reverse reaction, the reverse direction. And so this is an example of equilibrium where you're going from here to here, and then from here to like here, you're going back in the reverse direction. So you're dissolving, I would write this down. Third example, vapor pressure. If you guys remembered what vapor pressure is, let's say we have liquid. So let's say we have water, right? And then some of the water will evaporate, right? It's going to evaporate. So we call this evaporation. But then some of this gas is going to go back down and it's going to form a liquid again, and we call that condensation. And when you have both of these occurring at the same time, the same rate, then equilibrium is established. Sometimes you will see, sometimes you have a container and then you see some gas in the container, but then there's still water inside as well. Then that's an example of equilibrium. So you have both of them. It doesn't mean you have an equal amount of gas and an equal amount of water. No, no, no. What equilibrium is that the rate of the forward and the reverse reaction is the same eventually. And that eventually is equilibrium. So we can actually quantify whether the reaction is leaning or moving towards the right or to the left. For example, with the drawings that we did earlier, like are we forming more gas or are we forming more water? Like which of these two processes is more dominant? We do that using something called the equilibrium constant. The equilibrium constant is abbreviated as KEQ. So K is the constant, equilibrium constant, and then the EQ just represents equilibrium. So let's say we have a generic, this is a generic equation. So the way you solve for this constant is you're going to follow some rules. And the rule is that you're going to put KEQ, that's the constant, and you're going to start off with your substance. For example, C is going to, capital C is our substance. So you're going to put the concentration of one of your products. So you always start with products on top. So products here on top. So the concentration of big C to the power of this little c times, I know it says plus there, but that plus does not mean it's adding. It means that it's reacting, right? So it's actually multiplied here in the constant. And you're going to multiply it by the concentration of D to the power of little d. So the products go on top, and then you divide by the reactants at the bottom. So capital A, the concentration of the substance, to the power of the mole, so to the power of the little a, times the concentration of substance B to the power of little b. So this is how we set up the equilibrium constant, and you plug in numbers and you get a number. And I'll explain to you what that number means in a bit. So first we're going to practice setting this expression. Don't worry, it looks complicated, but we'll get it. You only include substances here that are not constant, that are changing. So substances that are constantly changing, constant. So it says here, the concentration of solids and liquids are constant and are never included in K. This means that the substances that are included are only the gases and aqueous solution. So I know it's a little complicated, but just keep this in mind, highlight this. Remember this, that only gases and aqueous substances are included. So here is our first example. It says to write the expression of K. So if you look at the state of matter, you have a gas, and that's all we have, gases. And gases are changing, right? This means that substances that are included are gases and aqueous substances. So we're going to use all three of them. So what you're going to do is you're going to write K, EQ, is equal to product, the concentration of our product, right? So our product is PCl5 to the power of 1. There's a 1 there, right? So we could just leave it as is because it's 1. And then you divide it by the concentration of the reactants. So here we have PCl3 and Cl2. Okay, so we don't have any coefficients in the front, and this would be our expression. And if we had numbers, we would plug them in and get another number at the end, and that would represent something, which I'll explain again later. So what we're going to do right now is we're going to practice setting up these expressions so that we understand that. So go ahead, if you're ready, go ahead and start doing these. Find the expression, and then you'll just try when you feel comfortable. I know you guys will get it. So if you look at this one, this first example, we have a gas, we have a gas, we have a gas. So all of them are included in the expression. In the second example, we have a gas, and a gas. So you'll include those in the expression. However, for these last two, we don't include the solid because that's one of the rules, right? So if you look at the rules, let me move this here. The rule says right here that solids and liquids are constant. They're not included. So you're going to ignore those. So you're going to ignore the solid. You're going to ignore this solid as well. You're also going to ignore this liquid. Okay, so just keep that in mind. So I'm going to do the first one. If you want to try it out, go for it. Press pause. So here we go. K, EQ is equal to the concentration of our product, which is water, right? It's a gas, it's a vapor. And there's a 2 in the front. Do you guys see a 2 there? So we're gonna raise this concentration to the power of 2. And that is all our product. So now we could divide. And we have our gases here. So we're gonna start with H2. Doesn't matter where you start. You could start with O2 if you want. But there's a power of 2 there, so we're going to put a 2 right there. And then we have oxygen, right? So we multiply, not add, we multiply by the concentration of O2, and there's nothing in the front. So that means that we could just put a 1 there or just ignore it because anything to the power of 1 is the same, right? So that's how you would write the expression for this first equilibrium reaction. All right, so I would recommend that you guys try the next one on your own. Press pause and then try again. Because if you don't try, then you're not going to get it. Learn from your mistakes, okay? So now that you tried, I'm going to write my expression, equilibrium expression. So products over reactants, so N2, concentration of N2. There's a 1 in the front, so there's no power really. And then you multiply by H2, raise it to the power of 3. Products on top, reactants at the bottom. Now I'm going to put the concentration of NH3 to the power of 2. Okay, so to the power of 2 right there. And that's how you would write the equilibrium expression for the second one. All right, now we're going to try the third one. Go ahead and try that one. All right, now that you tried, let's go over the answer. So according to our rules, only 2 types of substances may be included, and those are your aqueous substances and gases, right? So that means we have to ignore the solid. We're going to ignore this guy, okay? So we're going to write KQ is equal to products, right? Products. So concentration of calcium ion to the third power times, not add, times PO4 -3, which is phosphate. And you raise that to the second power. And most students get this wrong because they include this guy at the bottom. But look, it's not aqueous and it's not a gas. So you don't include that at the bottom. So this would be our answer. Okay, so that would give you a number. And again, that number represents something, which I'll tell you in a bit. Now go ahead and try this next one. Hopefully you could get this one right. Once you tried, let me know. So again, what should be included? Only gases and aqueous substances, right? So here we have a liquid, so we do not include that. And here we have a solid, we do not include that. We're only going to include the gas. So that means KEQ is going to equal to the concentration of O2. Okay, and that's it. That's all it is. And there's no power other than 1, right? So there's a power of 1. So whatever this concentration is, that's what the value of K is going to be. So what's the whole point of this? The whole point is this. What is the significance of that number? So if the number happens to be larger than 1, meaning that the power, maybe the power is like a positive number, then that means the products are favored. So if we have something that's larger than 1, then that means this is going to be favored, meaning you're going to have more of this, okay, and then less of that. Let's say for this reaction right here, let's say K is smaller than 1. It's a decimal, or it's a number that has a negative power. Then that means that the reactants will be favored. So these guys will be favored, meaning you'll have more of this. Remember, the rates are the same, but the amount is not. So this number represents that. So here is the last example, and this last example that I want to go over has numbers. Go ahead and try this, set up your expression, but this time plug in the numbers and see what you get. It's going to be a little tough to do because you haven't really done this, but I think some of you guys can do it. It says calculate the concentration of N2. So just think of that as a variable at the very end. Think of it as X at the very end. Okay, so go ahead and try and then check in with me, okay? Q. Products, which is NH3, to the second power over the concentration of H2 to the third power times the concentration of your other reactant to the first power. So that's how you would write the expression. Now the question says calculate the N2 concentration at equilibrium. So it wants this right here. So you want this. You want to know what the concentration of N2 is. So what is this concentration going to be at the very end of this reaction? If we know everything else, then we could solve. It says that KEQ is 626, right? So I told you, is the reaction going to lean to the right or left? it's going to lean to the right because this number here is bigger than 1. So this forward reaction is going to be favored. So I'm going to plug that in, 626 for KEQ. The concentration of NH3, it tells you right here, it's 0.0200, right? So I'm going to plug that in. And remember, it's a power of 2. And then I'm going to put 2 is 0.2 to the power of 3 times x. So you guys can replace that with x. I usually do that because it's just easier to see. And when you guys use algebra, again, some of you guys need to review this. I want to isolate x. And so, you know, because I know my math, my algebra really well, I could just swap this x with this 626. You could do that. So I'm going to do that. If you don't know this rule where you have something equal to some number that has a fraction or a denominator, and you should know that you can swap things that are diagonal. It's like cross multiplying. If you don't know how to do that, then just multiply by 0.2 to the third power on both sides, and then solve for x. So you could do that way too. So I'm going to swap x and 626. So x is equal to 0.0200 to the second power over 0.200 to the third power times 626. Okay, so do this in your calculator. You have to know how to use it, and you should get this number, 7.99 times 10 to the negative 5 power. So that is the concentration of N2. Okay, so that's what X represents. It's the concentration of N2.